So we started section 3.5 last time. We were looking at limits and infinity. And the piece that we had done, a couple of them anyway, is we talked about horizontal asymptotes. So horizontal asymptotes will happen when these limiting behaviors on the end actually approach a value, as opposed to sort of plummeting down or plummeting up. You know, plummeting is not the word there, but rising up forever. It actually levels off at some value. Those are horizontal asymptotes. And we talked about limits at infinity when we have this specific sort of a feature where we have a constant divided by a polynomial raised to a power. So x to the r is what they r is what they use here. Okay, and we had done one example. So our function on top was 5x cubed minus 3x squared plus 10x over x squared, and then we separated it into fraction pieces, right? And then we looked at each piece individually to see what would happen. So this first piece, 5x, that's infinitely large, so that's going to dominate the whole thing. And then I have just -3. The limit of -3 is -3. And then the 10 over the x is the one that goes to the 0 from that previous slide. So we're going to take the same function on top on this next one, but we're changing the denominator to be x cubed. So the first thing we'll do is to just write out what we have. So we have 5x cubed minus 3x squared plus 10x. And it's divided by x cubed. And we go about the process the same way in terms of manipulating this. We're separating it into 3 fractions. So I have 5x cubed over x cubed. I have 3x squared over x cubed. And I have 10x over x cubed. And that will be 5 at the beginning. I have minus 3 over x in the middle. And then plus 10 over x squared at the end. Okay, is that algebra simplification okay? Good. And what we're trying to do is we're trying to find the limit of this as, which one did it say? Yep, x goes to infinity. Just FYI, it could say x goes to negative infinity, and we would have to do it a little bit differently, but this one is infinity. So I have the 5. I have the 3 over x. And I have, sorry, that was a minus 3 over x. Try that again. And then plus 10 over x squared. Okay, so we do it piece by piece again. The beginning one, this 5, what's the limit of the 5? Actually, I'll write underneath. What is it? It's 5. Constants are constants. It doesn't matter if you're approaching x is infinity, x approaches infinity, or x approaches 2. If it's constant, it's constant. What about these other pieces, though? Those are zeros. That's what that theorem was that we looked at last time. Those are each 0. Good grief. Okay. So I end up with 5, and then I have minus 0 plus 0. Overall, then my limit would be a 5. So on this one, we actually do approach a horizontal asymptote. So what we had done last time when we were looking at the previous one is we looked at the graph afterwards. So let's do that next and confirm that it sort of makes sense visually from what we're finding from a calculus theorems standpoint, okay? So put the equation into y equals. So you have 5x to the third, and I'll put it in exactly like it started before I started manipulating. Minus 3x squared plus 10x. And divided by x to the third. I have no idea why this is so dark. I know I'm not remembering something. But every button I push doesn't seem to help anything. That's the focusing button. That's not it. Hang on. Think. That may not be any better. Is it any better with the single light on, or is it worse? Can you see this? It's worse. Wonderful. Okay, back to the dim light then. Sorry, guys. I'll have job. Good choice. Okay. So my window is just going to be the standard window, so zoom 6. And what we see happening over here is that the graph is decreasing and it looks like it's leveling out, right? And if you wanted to confirm this from sort of a numerical standpoint, because we've talked about things from numerical standpoints before, you could go into your table and you could put big values for x. Like you could make it go 10 and then 100 and then 1,000 and 10,000 and so forth. And do you see what's happening to the x or the y values? They're approaching 5. So you could confirm this from a numerical standpoint as well as the graphical standpoint, much like we did back in chapter 2. Okay. So that works. So it matters. It matters whether you're dividing by, why didn't it switch over? It matters what you're dividing and what you're dividing by. These pieces will change every time, so just because the limit's going to infinity, you can't really assume a whole lot. You have to do all the pieces separately to see what happens. Okay, so we've got a few other examples. I just wanted to do that example where I just showed you that the denominator changing can change the result drastically, right? So over here, this one was infinity, but then this one was 5. If I went one step further and I divided it by x to the 4th, the limit would be 0, just FYI. So it will change drastically. All right, so we're going to take a look at this one. Now, this one's a little different. This one says that the limit as x approaches infinity, if 3 minus 2x over 3x cubed minus 1. And it can't be done exactly like the last problem. How is it different in a way that matters? The denominator has what in it, Jackson? Not just the x, but a constant. So it has 2 terms, right? The denominator has 2 terms, or you could say that the denominator has subtraction involved. That would be another way of saying that. I can't just put them over, I could put them over 3x cubed minus 1, but they're never going to look like these pieces that are over a single term. It's not going to look like that. So the approach that we take looks a little bit different. All right, so what we're going to look for is we're going to look for the largest exponent on x, which would be an x to the 3rd. Okay, and what we're going to do is we're going to multiply the numerator and the denominator by 1 over x cubed. Whatever the largest exponent was, you're going to use that one. There are some variations of how to do this, but this one will work all the time to do this way, okay? And we're going to do, right, like what you did back in Algebra 1 in high school where you distribute things through, right? So we're going to distribute this through to each of the terms. So the limit as x goes to infinity. I now have 3 over x cubed. And then I have 2x over x cubed. I have 3x cubed over x cubed. And I have 1 over x cubed. Some of those reduce and simplify, some don't. So we'll simplify the ones that do. So the limit as x goes to infinity. So we have the first one that stays the same, 3 over x cubed. The second one would become 2 over x squared. On the bottom, this first one would just become a 3, and the last one would stay a 1 over x cubed. Does that look okay? But now, every single one of those looks like one of these, except for the 1. The 1 at the beginning does not, or the 3. What was it? 3? The 3. This piece doesn't, right? This piece is a constant. But everything but the constant piece looks like that feature. What that means is all of those that are written as something over x to a power all go to 0. Now it's important that we don't divide by an exponent too large, because if I had all 4 of these things going to 0, that would actually create a problem. I have 0 on top, but what do I have on bottom?
You have 3.
I have a 3, so I will have a 3. Adrian?
Why do they go to 0 again?
This was the theorem that we just did. This was the last time that we did it.
Okay.
Right? The limit's in infinity. If the limit as x approaches, it's this first one, as x approaches infinity of a constant over x to a power, then you will get 0.
Okay.
And the reason is because you're dividing by something that's infinitely larger and larger and larger, and you get infinitely smaller and smaller values. That's the reason. So,
Okay. Thank you.
You bet. So we end up with the 0 on the top, the 3 on the bottom, and that limit is 0. Okay, ready to try a variation of that? Yes. The answer is yes. Okay, what about this one makes it look different? Yeah, the square root. Okay, so while it is not true that you can separate the square root to be over each of the pieces that are underneath it individually, like that's not an equal statement, it is true that those are approximately the values that you have underneath there, okay? So I really have the square root of an x squared underneath the radical, and I've got this other x piece too. But this piece right here is equivalent to x. It is approximately, right? So I don't have a largest exponent of x squared. My largest exponent is really x to the 1. That's the exponent's 1. So when I'm looking at trying to multiply by this, I want to try and decide what I've got underneath the radical as the largest thing. And it is x to the 1. So I'm going to multiply by 1 over x. In the numerator, that's perfectly nice and friendly. I have just 1, right? X times 1 over x is 1. But I need to take that over x in the denominator and merge it underneath the radical. So how do I do that? Well, I square root and I square. Those are inverse operations, right? It's like multiplying by 3 and dividing by 3. If you multiply by 3 and divide by 3, you didn't change anything. So if I square root and I square, I didn't change anything. So why did I do that? Well, because I can't move it underneath the square root if it's not under the square root already. So I need the value, whatever I'm using, to be under a radical in order to to multiply it by what's underneath the radical. So now I can actually merge these two together. I have an x squared, and I have it times 1 over x squared. You don't necessarily have to write it this way, but I want you to see this is what's happening, at least. And then I have an x times the 1 over x squared. I had to write it underneath a radical in order to move it under the radical that was already there. Now then, I can simplify. I have a 1 on top. I have the x squared times 1 over x squared. That's a 1. And then I have x times 1 over x squared, which is 1 over x. Is that right?
Why are you saying that x is the bigger than x squared?
I didn't say x is bigger than x squared.
What did you say again? Could you repeat?
What I was saying is that I needed... Oh, goodness, that wasn't supposed to happen. What I was saying is that in order to multiply these together, I need them both to be under radicals.
Okay.
So I changed the expression 1 over x, to look like the square root of 1 over x squared.
Oh, okay.
Technically, the 1's squared, too. It's just that it doesn't matter, right? Because 1 squared's 1.
Okay, I see what you're doing now.
So I need it to be underneath a radical to be able to merge them. It's just a form issue. But this is good, because I have constants, a couple of them, and I have something over x. What's the limit of the 1 over x part?
0.
That's 0. So I have a 1 on top, and I have a square root of 1 on bottom. And what's the square root of 1? It's also 1. So this limit's 1. Okay, last one. All right, this one's got a sign in it. Sign is definitely not going to turn into a constant, ever. In fact, it's going to keep going up and down, oscillating. It doesn't get approaching anything. It's very unruly. Well, it's not unruly exactly. It's very predictable, but it's very cyclic, right? It's what it really is. It keeps this pattern going. So what we're trying to do, though, is to take something that's cyclic, goes between 1 and negative 1, it bounces up and down, and divide it by something that gets infinitely large. So the picture that you should probably have in your mind is that it's bouncing, but because we're dividing it by something that gets bigger, it's doing this. Does that make sense? Okay, it's oscillating for sure, and it's always going to be oscillating, but it's oscillating smaller every time because I'm dividing it by something bigger every time. That's a great noise outside, isn't it? Wow. Okay. So how do we show that this is happening? Well, I'll show you how we show it. So one of the things I already said is that we know that sine, it bounces up and down between -1 and 1. This is an inequality that says the same thing. Sine values are always between -1 and 1, and the 2x on the inside doesn't change that. It just changes how fast it's happening. Right? Makes it faster, makes it slower if we multiply by that constant. But the sine itself value is going to be bouncing between 1 and -1. And what we're going to do is we're going to take this triple inequality and we're going to divide each piece, there's 3 pieces, by n. X, sorry, different class. X. Now, that keeps my inequality the same direction because the x values I care about are positive. How do I know? Well, because it says x is going to infinity. Those are positive numbers. So I can divide by positive numbers and it doesn't change the direction of the inequality, right? If I were dividing by negative, it would flip the direction of the inequality. Okay? But do you see what's trapped inside the middle now? It's our function up here, right? That's actually trapped inside down here now. That's our goal. Our goal is to get what we want trapped in between. Now what we're going to do is we're going to take the limit of all 3 pieces. So we're going to put the limit as x approaches infinity of -1 over x. It's less than or equal to the limit as x approaches infinity of the sine of 2x over x is less than or equal to the limit as x approaches infinity of 1 over x. Okay? As long as we do something to all 3 pieces, that's an allowable operation. We did it with the division by x, making sure that x is positive, which it was, and then we're taking the limits. But take a look at that first limit and that last limit. Those are in forms that we are able to work with, right? What is the limit as x goes to infinity of -1 over x?
0.
It's 0. And what is the limit as x goes to infinity of 1 over x? 0. So what's squeezed in between has to be 0 as well. Okay, so all this right here means that the limit as x approaches infinity of sine of 2x over x is also 0, and that is called the squeeze theorem. The squeeze theorem says that if I can sandwich it, right, or I can squeeze it between 2 values that are exactly the same, then obviously it has to be the same value in the middle too. Any questions on that?